All right. The snowboarder problem is what we're going to work on in our computational exercise today. And so for the beginning part, the snowboarder drops some distance h. Oops. Okay. And then when they land at an angle like this. And by the time they drop some additional distance b here vertically, they no longer have a velocity perpendicular to the slope. Okay, so to describe this problem, we want to think about this rotated coordinate system here. And so over that distance b, their acceleration stops them from any longer having a normal velocity. And so after this impact, they're only moving down the slope along this x direction parallel to the slope. Okay. All right. We're also going to think about the beginning of this problem. During the drop, we'll think about a non-rotated coordinate system. Okay. So 3 things we want to find. 1 is speed at landing. 2 is acceleration during impact. And 3 is normal force during impact. And we're going to use these 3 results during the lesson today. Okay, so first, the speed at landing. To use that, this is a pretty straightforward kinematics problem, okay, that you've solved before. So I'm just going to point out that their initial velocity is 0. This is now just a one-dimensional kinematics problem where their acceleration is g. So the Vy at the end of that drop is just negative 2gh. Now this is in that black coordinate system, x and y, that are not rotated. I'm now going to use green to say that I'm switching into this rotated coordinate system. Okay, and so in this coordinate system, right, we can notice that this angle here is theta. That's the same as this angle here. Okay, and so in this coordinate system, the velocity of dropping, which looks like this, has 2 coordinates, one along the x-axis and one along the y-axis. For the beginning of this problem, we're only going to need to worry about the velocity along this rotated y-axis. So along this green rotated coordinate system y-axis, the y velocity is negative 2gh cos theta. Okay, the x is 2gh square root of 2gh sine theta, just for completeness. Okay. All right. So now we found this first thing. Second thing we want to find is the acceleration during impact. Okay. And so we're going to think about this as another kinematics problem where we want to know what's the acceleration along the y-axis. We're going to treat it as constant. Okay, we're going to assume it's constant, so really we're finding the average acceleration. And we know that the distance, the vertical distance covered during that acceleration is b, okay? But again, we're only thinking about the y-axis here, and so the distance along that y-axis perpendicular to the slope is given by basically the same part of the same geometry as the last part. So that distance is going to be b cos theta. Let me write this in a different place to make that less confusing. So we've got b here, b sine theta, b cos theta. Okay, so delta y is negative b cos theta, and this is just a 1D kinematics problem again. So we've got that the acceleration is y is, we're going to use our kinematics equation that does not require time. Okay, so we don't have to find the time. Our v final in y is 0, okay, because it's not moving perpendicular to the y-axis at the end of this acceleration. So that means our AY is negative 2GH cos squared theta over, there should not have been a G there in this last one. Sorry, it's just 2 delta Y. 2 cos theta. Okay, so these 2's cancel out. Our negatives cancel out, one of the cosines canceled out, and we get GH cos theta over B. That acceleration is positive, which is what we expect, right? Because he was dropping along that into the slope, and now they're no longer dropping into the slope. Okay, so this is our net acceleration in Y. And so we found that, and then now we can use that to find the normal force. Okay, so let's redraw the free body diagram that we drew in class on Friday. We've got the normal force pointing perpendicular to the slope, the gravitational force pointing straight down, and again, we're just going to consider forces along this y-axis. Okay, so our Fn y is just Fn, and our gravitational force along y is negative mg cos theta, right? So Fn minus mg cos theta is our acceleration along y, all right? So Fn equals mg cos theta plus gh cos theta over b. This should have been ma, not just a, mg cos theta. So then our Fn is mg cos theta times 1 plus h over b. All right, and that's the last of the results that you're going to need to have already found for the assignment today.